Well, good morning, everybody, and welcome to day 255,642 aboard the Axiom. As always, weather's a balmy 72 degrees and sunny, and oh, hey, I see the ship's log is showing that today is our 700th anniversary of our 5-year cruise. Well, I'm sure our forefathers would be proud to know that 700 years later we'd be doing the exact same thing they were doing. So, be sure next mealtime to ask for your free Septuacentennial cupcake in a cup. Wow, look at that. Also today we have a, hey, Otto, what's that flashing button?
That alarm you're hearing is the fact that we are now done the AP test and we could start learning about other topics. Hopefully things that you'll find useful and also interesting. Today we're going to start looking at relativity. I was so excited to teach this to you guys all year. I know some of you guys love these modern physics ideas, and I think this will be no exception. So I want to start by making sure you understand that relativity talks about relative to what. And what that means is that oftentimes when you get a measurement or a number or an answer, and we think that answer is true, you should realize that that truth might be a relative truth, meaning that that number may only be true relative to some other thing. And I know that might not make sense yet, but you'll see as we go through this, when we talk relativity, we're talking in reference to something else. So what you really want to do is you want to think about this idea, frames of reference. Whenever you take a measurement, whether you realize it or not, your measurement might depend upon the frame of reference that you're in. So in this picture, we have a woman zooming by a factory on a train. And there are two main frames of reference here. There's the frame of reference of the earth that the factory is in, and then we have the frame of reference of the train that the woman is in. And based on your frame of reference, you might see things and describe things and measure things differently. So this woman looking out would see the entire earth and all the things on it, like the factory, zooming to the left. She would describe the motion of the factory as a negative velocity heading at a certain speed to the left. She would describe this solar charger as at rest. In her frame of reference, this is not moving. Someone on Earth looking at the solar charger, they would see that moving to the right along with the rest of the train. So their truth depends upon their frame of reference. Their measurements, their description of what's happening depends upon their frame of reference. Here's an example of this. We're going to have two main frames of reference here. We're going to have the frame of reference of the bus, and we're going to have the frame of reference of kids off of the bus. And I don't know if you saw, but something really weird happened when Sally began to sally toward the back of the bus. And if you watch carefully, watch the scenery behind her as she walks. So keep your eye on the tree, keep your eye on the bus, keep your eye on Sally. And hopefully you can see that as Sally walks backwards on the bus and the bus moves forwards, that if they have their speeds matched just right, it's going to appear that this tree is at rest relative to Sally. For the rest of the kids on the bus, they're going to see that tree moving. For the people who were on the ground at that gas station, if they were able to see into this bus and see Sally, they would see her at rest. As the bus went forward and she went backward, she would stay lined up with those kids that were standing by the gas station. So again, how you describe things, how you measure things, depends on your frame of reference. The first people to realize this were two scientists from the 1700s. Okay, we got Galileo in the 1600s. We got Newton in the late 1600s, early 1700s. And they came up with this idea of relativity. You'll sometimes hear it referred to as Galilean relativity. He's the first one who did it. You may hear it as Newtonian relativity because he refined it. Or I think the best way to describe it is to call it classical relativity. Classical relativity is going to jive really well with your common everyday experience. When we get to modern relativity that was developed by Einstein, things are going to get crazy. We're not going to get there today. We're just laying the foundation today to understand why Einstein's ideas are so earth-shattering. We want to start with this idea of invariance. And an invariant is some property that when you measure it, you get the same answer regardless of what frame of reference you're in. So invariants are things that don't change based on your frame of reference. It turns out in classical relativity, there are three invariants. They are mass, time, and distances. So if I had this baseball on a bus or a train or any other frame of reference, and someone was measuring the mass of the ball from the train's frame of reference, or from the Earth frame of reference, or from any other frame of reference, they would all get the same value for the mass of the ball, 141 grams. If I took the ball and I was on the train and I dropped it, and I timed how long it took to fall from my hand down to where I caught it, that time would be the same whether or not I was on the train timing it, or on the side of the railroad tracks timing it, or on a helicopter flying by timing it. Everybody observing that event would see the exact same amount of time pass from the start of the event to the end of the event. Finally, distance. If we were measuring the size of the ball, regardless of what frame of reference we're viewing the ball from, the size of the ball would be exactly the same. These are the three invariants for classical relativity. One thing that's not invariant, that's really easy to look at, is this idea of velocity. Velocity is not invariant. Different frames of reference will measure different velocities for objects' travel. So for instance, we've got a few characters from The Simpsons. Professor Frink in his Frinkmobile going 50 meters per second to the left. We got Homer in his really cool car going 30 meters per second to the right. We got Bart 5 meters to the right. And we got Nelson Muntz, who happens to be standing behind the wall, not moving relative to the wall or the earth. These speeds that you see are not the real speeds of the object. They are the speeds relative to Nelson Muntz. They are the speeds relative to the earth. They are not the speeds that would be viewed by these other people. They would not be the speeds viewed by somebody who is watching this from some other frame of reference. So realize, even though we might think Nelson is at rest, realize that Nelson is on the earth, and the earth itself is moving. It's spinning, it's going around the sun is going around the galaxies are moving away from other galaxies. And not only that, if Homer Simpson was looking at Nelson, he would not see Nelson at rest. He would see Nelson moving at 30 meters per second to the left. So the speed that we measure is determined by our frame of reference. No answer is correct for all frames. This 30 meters per second is only true for Nelson's frame, for the frame of reference of the Earth. Bart and Frink, they would see different speeds. If Frink was to measure the speed of Homer's car, he would see it going 80 meters per second, right towards him. these two speeds would combine together. So realize that relative velocity means that whenever you say a velocity, technically you should specify the frame of reference. Most times the frame of reference is relative to the Earth, so we don't really need to do it. It's kind of inferred, but technically, to be correct, a velocity is only correct when you relate it to the frame of reference where it was measured. So here we have a silly little video. We got the community members in Springfield moving their town from one place to another because they polluted where they originally lived. And you can see Homer was able to go straight from his house to Moe's because the relative velocity between those two objects was 0 meters per second. They were moving at the same speed down the road, so the relative velocity was 0. Okay, we can see this really well if we look at somebody in an enclosed system with no windows, so we have nothing to judge other than what we see in our own frame. And this is an example of an astronaut in the International Space Station. Just like me, she has some baseballs. She's from Europe, so she calls them baseball balls, which I guess is really the correct term. And she's going to see these balls at rest, or very close to rest when she lets go of them. Realize the space station itself is moving at thousands of meters per second. And those balls are moving with the space station. But relative to her, those baseballs are at rest. So which is the correct speed? The 0 meters per second that she measures? Or the 7,000 meters per second that I measure when I look up and see the space station moving? The answer is they are both correct. Speeds, velocities I should say, are relative to the frame of reference where they're being measured. No frame of reference is preferred over any other frame of reference. However, there's a caveat to that. The frame of reference must be non-accelerating. If your frame of reference is accelerating and you had the baseball here, you would see this ball displaced from equilibrium. If it was speeding up, it would go one way. If your frame of reference was slowing down, it would go the other way. If your frame of reference was turning, you would see it deflect right or left or in some other direction. So the idea is non-accelerating frames of reference will all be equivalent to each other. That is to say, there's no way to tell whether or not your frame is moving or not. For this astronaut, she has no way to tell whether or not her frame is stationary or moving at a constant speed. Okay? The only time you can tell if your frame of reference is in motion is if that frame of reference is accelerating. And if it's accelerating, you're not going to measure things in the normal way. So for instance, if we have a train driving along at a constant speed, and someone in the train throws the ball straight up and down, they're going to see the ball travel straight up and straight down, and all the laws of physics that we learned will work just fine. If, on the other hand, you're standing on the side of the train tracks and you're watching the person and they throw the ball up, they're not going to see the ball go straight up and straight down because the train's moving. So when the ball gets thrown up, it will continue to move forward. And then when it comes back down, it will continue to move forward. And this person would see the ball travel in a parabolic arc. So both people describe a different path to the ball. But both of them would have the same laws of physics. One would see it more like a projectile, one would see it more like free fall, but the same laws of physics would be determined in both frames of reference. Both frames of reference are equally valid at describing what is happening. This person can't say definitively that they're the one that's at rest. This person can't definitively say that they're the one at rest because they're both in non-accelerating frames. If, on the other hand, this train were speeding up or slowing down, then this person would be able to tell that they were in a non-constant speed environment. And then things would be totally different. They would be able to tell that they were the one that was accelerating. This person would be able to see also that this person was accelerating. But as long as there's no acceleration, all frames of reference are equally valid. Here's an example that I kind of ran across by accident when my son was younger. I took him to the Strasburg Railroad in Pennsylvania, and I was filming the trip because he liked to watch it afterward. He was really young, and he liked watching these kind of videos of things that he had done. And when I filmed this, it happened to be at a spot where our train is moving this direction. There was another train that was sitting still on the side of my train tracks. I want you to focus on the other train, and I want you to realize that there's no way for you to tell whether or not my train is moving or that train is moving if all we are doing is focusing on that one other train. My forward motion in this direction is equivalent to the other train moving this way. So here it was easy to tell because you could see the background, but just focus on the train. Right now you can't tell whether or not they're moving left or I'm moving right. I knew that I was moving right because I was able to see the background, but don't focus on the background, just focus on this train. And if you're in that other train, you would see the same thing I am. You'd see one train moving relative to the other, but you can't tell which train is actually the one that's moving. Again, try to focus your energy on the train itself. There is no way to tell which train is moving and which train is at rest. And then the amazing part is when I passed this train, I found out that somewhere along the way during this video that my train had stopped moving and the other train had started moving. This was such a gradual transition that I felt none of it, but it showed me really well that all motion is relative and that no frame is better than another. And again, the caveat there is so long as your train is not speeding up or slowing down. Mine slowed down so gradually I didn't notice it, but had my train slammed on the brakes, I would have felt myself lunge forward. I would have known my train was the one that was moving and changing speed. Same thing on the other train. So long as they started up really gradually, they would not be able to tell whether or not it was their train that was moving or mine. So anyway, I know we haven't got into anything too earth-shattering yet, but I wanted to lay the foundations of frames of reference and relative velocities and invariants before we get to the stuff that's really weird. Anyway, I hope you guys did great on your AP test, those of you who took it, and I look forward to teaching you some new material over these next few weeks.